This presentation continues the series on multiple regression and focuses on the statistics we use to assess the fit of the regression model. Because we have multiple predictors in multiple regression, we have two levels of analysis or two questions of research interest. The first level of analysis concerns the overall set of predictors. It considers whether or not the model successfully predicts the criterion or the extent to which the model fits the data. The second level of analysis concerns the individual predictors. Here we will consider whether or not all predictors significantly predict variance in the criterion, whether or not all predictors are needed to adequately predict the outcome, and whether or not experimental variables are significant after the contribution of control variables has been considered first. We will start our discussion by considering the first level of analysis, the fit of the model to the data. In multiple regression, we will compute the correlation the set of predictors has with the criterion, and this will be called the multiple correlation coefficient, or big R. By big R, I mean uppercase R. Unlike bivariate R, big R does not assume negative values, and it tells us the strength of the relationship between the predictors and the criterion. Because it is the result of the contribution of multiple predictors, big R will always be larger than the largest bivariate correlation of the predictors with the criterion. In multiple regression, the most important statistic used to assess the fit of the model is big R squared, or the coefficient of multiple determination. It will be interpreted directly as the percentage of variance in the criterion predicted by the model or set of predictors. Because big R squared is a bias predictor of the population parameter, many researchers will report the adjusted big R squared. The smaller the sample, or the higher the number of variables, the more likely it is that the sample big R squared will be biased. You will be able to interpret big R squared or adjusted big R squared as the percent of variance in Y predicted by the model. The percentage of the variance in the criterion not predicted by the model is quantified by the coefficient of multiple alienation, which equals 1 minus big R squared. This diagram helps visualize the prediction of Y by a model. Although the partial regression coefficient is based on the unique variance in Y predicted by a single predictor, say the area U2 for predictor X2, big R squared considers all regions of Y predicted by the model, both unique and redundant portions of prediction. Note that the coefficient of multiple alienation equals the variance in Y not predicted by or shared with the model. The typical research hypothesis involving multiple regression is that the model will predict variance in the criterion. So consequently, the null hypothesis concerning model fit is that the model fails to predict variance in the criterion in the population. This will be tested with an F statistic with degrees of freedom in the numerator equal to the number of predictors in the model, and degrees of freedom in the denominator will be equal to the sample size minus 1 and then minus the number of predictors. The F statistic used in regression and ANOVA procedures. Specifically, the F is the ratio of two estimates of variance. In the numerator of the F ratio will be a calculation of variance associated with treatment, while in the denominator of the F statistic there will be an estimate of error variance. Results of the use of an F statistic are typically presented in a summary table, which will be taken up on the next slide. Here is a summary table for a model in which 3 quality indicators were used to predict 30-day rehospitalization rates for pneumonia patients. Rehospitalization rates are an outcome of hospital quality measured by Medicare. Higher rehospitalization rates are interpreted by Medicare as indicating poor quality of care in a hospital. The first column of the summary table indicates the source of variance used in the calculation of the F statistic. In analysis of variance and regression statistics, we will partition total variance into two basic components: the variance due to the treatment or regression, and variance due to error or residual variance. This is directly related to our partitioning of total variance into the portion of variance predicted by the model, which is the coefficient of multiple determination, and the proportion of variance not predicted by the model, which is the coefficient of multiple alienation. The next column in the summary table contains the degrees of freedom associated with total variance and with the two component parts of regression and residual. Note that the degrees of freedom for total variance is the sample size minus 1, and that the degree of freedom for the regression source of variance is the number of predictors in the model. Finally, note that the degrees of freedom for error variance is equal to degrees of freedom for total variance, or n minus 1, minus degrees of freedom for regression or treatment, which is p. Please note that df total is equal to the sum of df regression plus df residual. The next column of the summary table reports the sum of the squares, which you will remember is the numerator of the variance. Please note that just like degrees of freedom, sum of the squares total equals the sum of sum of the square regression or treatment and sum of the squares error or residual. The next column reports the mean of the sum of the squares, ms, which is derived by dividing the sum of the squares for a particular source of variance by degrees of freedom. You might remember this is exactly the formula for the sample variance, sum of the squares divided by degrees of freedom. Thus, ms is another name for the variance and represents the fact that the variance is the mean of the sum of the squares. We will only compute the variance for regression and for residual in a summary table. The next column reports the F statistic, which is equal to the regression variance divided by the residual or error variance. So like all of our test statistics, the F is a ratio of an estimate of treatment to an estimate of error. The final column reports the probability associated with the test statistic. Since the probability is less than alpha, we will reject the null hypothesis. You can also obtain the critical value by consulting the F table using 3 degrees of freedom in the numerator and 4050 in the denominator. Once we look at the F table, we discovered there is no row for 4050, but the next lowest degree of freedom for the numerator is 1000. If we look at the intersection of 3 degrees of freedom in the numerator with 1000 degrees of freedom in the denominator, we find the critical F value equal to 2.61, which clearly exceeds which is clearly exceeded by the test statistic of F equal 10.27. A final thing to consider in this table is the computation of the coefficient of multiple determination. As suggested by the visual model we looked at earlier, it is the ratio of the sums of squares treatment or regression divided by the total variance. By dividing sums of squares regression by sums of squares total, we get r squared equal to 0.008, which is the proportion of total variance attributable to or predicted by the model. Finally, this finding can be interpreted by saying that the null hypothesis that the model fails to predict variance in the criterion in the population is rejected because the probability associated with the test statistic is less than alpha. The model predicted 0.8% of the variance in the criterion. Please note that there is no reference in this interpretation to the direction, as big R only captures positive values, and consequently there's no directionality to how the model predicts variance in the criterion.